All right, it's 11 o'clock. How is everyone doing?
Doing all right.
Good. So questions, any questions over anything we did last time or homework questions? Everybody's happy?
Was able to either work it out or figure it out because of your video.
All right, well, we are done with the techniques of integration. There's nothing left for us to discuss. We, in theory, have everything that a Cal 2 student is equipped with in order to find antiderivatives, all right? And now we're gonna start, we're actually gonna take a few steps back. We're gonna go back into chapter 5, and we're gonna start talking about how we use integration to do something, right? The book is a little weird. Not weird, it's just most books do this. They talk about the antiderivative, then they tell you how it's used, and then they go ask you to learn the techniques of integration. We do it a little different. We do, hey, here's the idea of the antiderivative, let's figure out how to do them. And now we're gonna go back and talk about how we use it, all right? So today's gonna be kind of a weird day because I'm actually gonna be pulling material from all these different sections. And so your homework, this says 5.5, 6.1, sorry, where is it? 5.2, 5.3, 5.4, and it says homework to be announced. So I will talk about what homework you should do for today, for today's material. I'll talk about that at the end of class. All right, let's get to it. So let's start off with this concept of Riemann sums. Now, this is covered in Cal 1 sometimes. I know in my Cal 1, I don't cover Riemann sums, but here we're just going to talk about them briefly. We're not going to go through, a week or two of doing Riemann sums by hand. It's just more to get the fundamental idea of what a Riemann sum is. So I've got some visual guidance here that will help us kind of understand what's happening with this idea of a Riemann sum. And it goes back to the fundamental problem that humans ran into at some point when they were trying to calculate the area of a circle. All right, so, for a long time, humans had no problem calculating areas of things like rectangles, right? We had a very, very solid idea of how to figure out this area. And that's, whatever this is called, this, length and width. The area would just be the length times the width, and that's it. We're done with that. We're happy with that. And if you had more complicated objects like a triangle, then we had ways of doing that also, right? Triangle 1/2 base times height. So we could handle polygons, even if it was some really weird shape like this. We could figure it out by maybe divide and conquer. We could break it into smaller like triangles like this, and then calculate the area of each triangle. I mean, so you have to imagine like humans hundreds, thousands of years ago trying to parcel out land, right? Trying to figure out, okay, this is my land, goes from here to here, how much area do I have? And so we did pretty good with these shapes, but there were other shapes that were much more difficult to do, shapes that would be, maybe you had like a river running against your property, right? And you had to figure out like, what's the area of that? So we had curves instead of straight lines. And that became very problematic. We could estimate it, but we really wanted to have a more precise way of doing it. So it brought us back to the circle is really where the first idea of trying to get the area of something with a curve to it comes from. And so there's many ways to approach this. One way to approach it would be to do what the Chinese did. And what the Chinese did was they said, okay, we're going to take a circle. And they knew the radius, right? So they would know whatever the radius is, call it R. They knew what that was because they could just put a stake in the middle of the ground and a rope or a string, and they could draw out a circle. So they knew the radius, they just didn't know what the area was. So what they would do is this, they would they would break up the circle. They would draw a square or a rectangle within the circle. Then they would draw maybe another rectangle here, and then another rectangle here, another one there, another smaller one there, maybe squeeze another one in here, do another one there. And they would do that all around the circle. They would have all these rectangles, and they would add up the area, right? So you just imagine adding all these up. So let's say we take all these rectangles, add them up, and we get some area. I'm going to call it the area of the rectangles in. You'll see what I mean by that. This is the area of the rectangles in. Do y'all agree that that area would be less than the true area? Because you're going to have a bunch of little gaps. You couldn't get these little corners, right? So you know that you're missing some area. So whatever area you got from the rectangles on the inside, that's less than the true area. And then they would basically do kind of the opposite. They would draw a square on the outside. They know the area of that, right? And then they would start drawing rectangles and subtracting that area from the big square. All right. And if they did that, right, take the area of the big square and start subtracting out these rectangles in the corners, then that area, right, of the rectangles outside, right, being subtracted from the square, that would be bigger than the true area because, again, you'll have these little gaps, these little pieces you didn't account for. So they would be able to somehow squeeze the true area between two numbers. And the more precise they got with their measurements and the more rectangles they added, the smaller that window became. And they were actually able to determine that the area, the true area, is really, really close to 22/7 times the radius squared. That's what they were able to use as an estimate. So if you get on your calculator and do 22 divided by 7, let me see what we get here. 22/7, this is approximately 3.142857 r squared. And that's really close to the true area, the true area that we know today. The true area is what? Pi r squared, right? And pi, right, if you do pi, it's what, 3.14, oops.
3.14159.
14,
As far out as I know.
Yeah, we'll just go there. But you can see here that the Chinese estimate was within within 2 decimal places of the true area. So that's pretty precise, right? They've got it down to the 100th, which is pretty good. I mean, but it's not correct.
In all practical purposes, you only need it out to 3.14. So
yeah, well, it depends. It depends on how precise you need to be. But for their purposes, that was good enough for most things they were doing. Now, this method of filling this thing with rectangles and then, drawing a square and subtracting all those rectangles, this method has a name. Okay, this is called the method of exhaustion. The method of exhaustion. As you could imagine, that would take a long time, and you'd be pretty exhausted after all this, right? Got it? Understand? So that's where the fundamental idea came from, all right, of trying to figure out the area of something with a curve. That then, led to many other things, but one thing it led to was, well, you know what? Instead of trying to find the area of a circle, what if we're trying to find the area under a curve? So let's take this picture here. So the curve I have here, the function we're looking at here is the function f of x equals x squared, and I'm looking at it on the interval 1 to 5. That's this blue curve here, okay? And I'm trying to figure out what the area underneath this curve is, all right? So one thing I could do, okay, because I know the value of the function, one thing I could do is I could go to the right endpoint, 5, right? And I know then the width of this is 5. And I could plug 5 into the function. So if I plug 5 into the function, I get this point up here. This is the point 525. I know that the height of this then is 25, right? And then 5 times, I'm sorry, this distance here is not 5, it's 4. I apologize. We're going from 1 to 5, right? So the width of this rectangle is 4. The height of this rectangle is 25. And so an estimate would be 100. And that would be a real shitty estimate, wouldn't it? Because it's the area of this whole thing, and all I want is the area of this. I have the computer calculating the true area for us. Now, don't ask where that's coming from right now, but the true area is 41 1/3. That is the true area. And our estimate here is 100, and that's pretty bad. That's a bad estimate, right?
I'd say a much better estimate is, well, it's about half of the rectangle, so 50.
You could do halfway up, right?
Yeah.
You do halfway up. That would be one way you could do it. But here's the way we're going to approach it. Instead of doing this, we're going to take that, and instead of doing 1 rectangle, we're going to do 2. Okay. So what we'll do is we'll go halfway, and we'll go to 3. Plug that in and get this point. This is the point 3. Well, when you plug 3 in and square it, you get 9. So we know this height here is 9. And we know this distance from here to here now is 2, because you're only going from 1 to 3. And so this area is 18. With me? Again, it's more than the true area is here. We have an overestimate, but it's not as bad as the other overestimate was. And then we do the same thing on this one. From 3 to 5, that would be 2 again, right? And then this height we already said was 25. So 2 times 25, that's 50. And so the area together, that'd be 68. And remember, the true area was 41 1/3. So it's better, right? That's better. So what would be even better than this?
Breaking it up again.
Yeah, why don't we do more than 2 rectangles? Why don't we do 3? So here's what happens if I do 3. The true area now, I mean, sorry, the estimated area, I know this is hard to see, is 58.5. Let's just look at these. Well, you know what, let's go to 4, because those are kind of tough to, let's go to 4 rectangles. Now it's 54, it's even closer to 41 1/3. The distance from here to here now is 1 on all of these. 1, 1, 1. And then the heights are, 25. And then this one I'm plugging in 4 to get this height. So this is 16. And then this one right here is 9. And then this one right here is 4. So I'm doing, 4 times 1, that's 4, then 9, then 16, then 25. Adding those together, I get 54. So 4 rectangles, was better than 2. 2 was better than 1, right? Well, it's kind of like the method of exhaustion now. How far am I willing to go, right? If I do more rectangles, you see what's happening to the error, right? Our error is this region here. This is the stuff that's too much, right? We're overestimating. But as I do more and more rectangles, I'm getting less and less error, right? Look at that error start to go away. I'm at 30 rectangles. 30 rectangles. Keep going. Let me go to 50 rectangles. Okay, I went too far. It's 55 rectangles. Look at this look at the number here. Our estimate is 42.2. The true again was 41 1/3. So we're getting there, right? We need more though. How many though? How many do you go? Well, what do we have in calculus? What is the heart of calculus? In Cal 1, where did all this calculus launched from this one idea of what?
Find the slope of the tangent line.
Okay, but where did that come from?
The limit.
Derivatives?
Derivatives came from the limit, right? The limit was the whole basis of where we started in Cal 1. And what the limit allowed us to do was let X or something go to a number, right? but we were also able to let x go to infinity, right? We were able to let things go to infinity and then ask ourselves, what happens when you let that go to infinity? That's exactly what we want to do here. To get the true area, we want to let the number of rectangles become infinite. And if you can imagine that you have an infinite number of rectangles in here, then how wide is each rectangle? Well, the more we have,
zero,
the more
right?
narrow, right? So what's that, Hunter?
In their width approaching zero?
It's approaching zero. It's never getting there though, right? It's approaching, approaching. And in Cal 1, we did limits where things approach zero, and we got numerical answers. Even though something was approaching zero or infinity, we get numerical answers. So the idea here is, can we figure out a way to add up the sum of all of these rectangles in some infinite way? Does that make sense? Like just geometrically, like the basic idea of what we're trying to do? Okay, and that's what Riemann sums are. Riemann sums are us trying to add up a bunch of rectangles together. So let's go and take a look at how we're going to do this. All right. So before I proceed, I want to just share some notation with you. Probably saw this in college algebra. This symbol right here, that's the capital S Greek symbol, right? Sigma. It's just a Greek letter, okay? It's just a Greek letter. It's capital S. But in mathematics, this is what we use to represent sums. It's a way that we can write something out in a condensed form. For example, if I wanted to write out 1 plus 2 plus 3 plus 4, and I wanted to stop at, let's say, 1,253. Instead of writing that all out, here's what I would do. I'd write sum. I could use any letter here, so I'll put K. K equals 1 is where I want to start, and I want to stop at 1253. And what I want you to do is add up whatever K is. So this number on the bottom is what we call the starting index. And then up here is the stopping index. And then this right here is kind of like the argument of a function. It's the thing that you're actually going to calculate. So the first thing you do is you start by letting K be 1. So I'm going to replace that K with 1. I write that down. Then I say plus, because it's a sigma that stands for sum. Now I say plus, and now I let K go up by 1. So now I let K be 2, and then plus, and now I let K be 3. And I keep doing that until I get to my stopping point of 1253. Here's another one. Let's say I wanted to do 1 plus 4 plus 9 plus 16 plus out to 100. Well, I would look at that and I would recognize that these are all perfect squares. This is 1 squared, 2 squared, 3 squared, 4 squared, and it looks like I go all the way out to what? 10 squared? Right? So I could write it like this. K equals 1 to 10 K squared. That would be the formula for that. Now, it doesn't have to be numerical. It can be symbolic. So I could do something like this. What if I wanted to do, here, this one will be interesting. What if I wanted to do a sub 1 plus 3a sub 3 plus 5a sub 5 plus 7a sub 7 plus, now let's say I didn't want you to ever stop. I just wanted you to do that forever. So here's the way I'd write this. Sum K equals, well, it looks like I'm starting at 1. I'm not sure where I'm going to stop. Oh, where am I going to stop? I'm never going to stop, right?
Yeah, infinity, right?
But I'll put infinity here, and I'll put 1 here. Now here's the tricky part. You got to figure out kind of like a formula or a pattern to create this. So I noticed that every one of the numbers that I have here, 1, 3, 5, 7, those are all odd numbers. So here's how I can create a list of odd numbers. I can put 2k. 2 times k should give me all the even numbers, right? Think about that. If I let k be 1, it's going to give me 2. If I let k be 2, it's going to give me 4. K be 3, it's going to be 6. Understand? But I want the odds, so I'm just going to add 1 to each of those numbers. Now, this is not going to work yet. Look, because if I let k be 1, what do I get? K is 1, I get 3, don't I?
Yeah.
I don't want to start at 3, I want to start at 1. So what I can do is adjust my formula and make it 2k minus 1. Now, if I plug in 1, I'm going to get 2, then take away 1, and that's going to give me 1. If I plug in 2, I'm going to get 4, and I take away 1, that gives me 3. Make sense? Now, I'm not done. I have to put a subscript 2k minus 1 as well. And that would be the generic sigma notation or summation notation for this sum. That's all we have time for in terms of reviewing or talking about sigma notation. I'm going to use it right now, so I just want to make sure you have some little inkling of what it's about. All right, y'all ready? This is going to be kind of interesting. This is not something I would test you on. This is really more to just get you to understand like the power of what you can do with your mind if you just think through something. All right, so here's the idea. I have a function, okay? I have a function, some random function. I'm not even going to tell you what it is. It's just some function. I'm going to say it starts here at A and it ends here at some point B. And this is the function F. And what I'm going to do is I'm going to start cutting it up into rectangles, right? Cutting it up into rectangles. So I'm going to have some rectangle. Let's cut it into n rectangles. I'm going to do n rectangles. So I'm not going to tell you how many I have, just that there's n of them. So back in this picture here, when we had 2 rectangles, I cut this section between 1 and 5. I cut it into 2 pieces, didn't I? So the way you could think about that is, well, first, how long was it to begin with? Well, that's 5 minus 1, right? Which was 4. That's how wide that was, the whole thing. And I cut it into 2 rectangles. So if I take that and I take that 4 and divide it by 2, that's how wide each rectangle is. Agreed? So first I figured out the distance, the total distance between the first endpoint and the second endpoint. Whatever that distance is, I divided it by the number of rectangles, and that's how wide each rectangle was, right? That's how many sections I have. So in my picture, if I cut this number line into n equal pieces, now I can't really tell you how many, just that there's n, right? How can we determine how wide each of these are? How wide is each one?
Would be b minus a over n.
Yeah, you take the difference of the x coordinates. You take this x coordinate, subtract this x coordinate, like the 5 and the 1. We did 5 minus 1. Here we would do b minus a. And then you divide by the total number of rectangles, and that would be n. This is the width of each rectangle, right? Each one of them has that width. Agreed? All right, let's look at the very first rectangle. The first rectangle, what I'm going to do is I'm going to go to this right endpoint right here. I'm going to go up to the function right there. Boom. I'm going to plug that in and I'm going to draw a rectangle that goes over and down. Okay. Let's talk about the area of rectangle 1. We'll call that the area of rectangle 1. So here's what we know. Area is length times width. Right? We know how wide it is, right? How wide is it? What we just said, right? B minus a over n. I'm going to put that over here. B minus a over n. That's the width of this rectangle. What about the height, though?
Wouldn't it just be f of that point?
It would be f, right? It would be whatever this height is right here, right? That would be the function when you plug in that right endpoint, correct? Okay, but we have to figure out what that right endpoint is. We have to figure out what it is. So I'm going to do it down here. I'm going to just magnify that line. Here was A, right? Here was B. Here's that first rectangle, that point I'm talking about. My question is, what is this, right? What is the x coordinate of that? So do you agree it's this? It's whatever A is plus the width of the rectangle. Isn't it? Like the rectangle is B minus A over N, right? So it's like this point right here in yellow, that x coordinate is actually this x coordinate plus the width of the rectangle, which would be the B minus A over N. Y'all agree with that? So the area of the first rectangle should be this. It should be F with A plus, I'm going to need more space here. I should have given myself more space. A B minus A over N being plugged into the function, and then you multiply times the width. Everyone see that? Height of the function at that point times width of the function at that rectangle, right? That rectangle's width. Multiply those together, that'll give you the area of the first rectangle. With me? Let's talk about the second rectangle. Area of rectangle 2. Okay, well, it again will have B minus A over N because that's how wide it is, right? That's the width of it. But the height, now we're at this second endpoint, we go up, we go over, we go down, right? Let's look at that on this number line. Let's say this is the second point. Well, isn't it just this point with another width added to it? Isn't it just this one with one more of these B minus A over N's added? Right?
Yeah.
Do you have questions? I know some of you are getting this. Does anyone have a question? I'm going to look at it this way. I'm going to say it's A, okay? It's this original point plus 2 jumps, 2 widths, right? It's 2 jumps of the width. So I'm going to write it like this, plus 2 of those B minus A over N's.
But how do you know that's exactly the amount of distance? Like we can go shorter or longer.
I have fixed the number of rectangles at N right now. N
Oh,
is
that
a
makes sense.
fixed number, right? N, once I tell you I'm doing N rectangles, then we know what it is. Could be 100, could be 1,000, could be 4, could be 1,000,000. But N is some number, right? Some whatever number it is. So that as soon as I fix N, I then have fixed the width of the rectangle. And it doesn't change yet. Okay. So here's what the function is now. It's F with A plus 2 of those jumps to the right. Now I go for the area of the third rectangle. Well, I'll still have B minus A over N over here, right? It'll still be the function plus, the function evaluated at A plus, now instead of going 2 jumps, I'm going to go 3. So now I go 3 jumps of B minus A over N. Are y'all following the pattern here? The area of the fourth rectangle will be F of A plus now 4 jumps of that width times the width of the rectangle. So each one of those is a height times width, height times width, height times width, height times width. And in all of them, this never changes, right? The only thing changing in any of this is this number. That's it, right? That's the only thing changing. Let's keep going. What happens when I get to the nth rectangle? what is the area? So this would keep happening. When I get to the area of the nth rectangle, we should have f of a plus n jumps, right? N jumps of b minus a over n. Hey, where should we be when we get to the end? Where should we be? Where should we actually be when we get to the end of it, to the nth rectangle? What should our
Yeah,
x
you should be at B, yeah.
We should be at b, shouldn't we?
Yeah.
And do you see that if you cancel these n's,
Oh, yeah, it all cancels out, so you just have B.
you have a plus b minus a, and that just gives you b.
Ha.
So we are at the right endpoint. We are at f of b. Okay. Y'all good? Do y'all understand this? So if I want to find the area, right? If I want to find the approximate area, right? The area will be approximately equal to the sum with k equals 1 to n of all of the areas of all those rectangles r sub k. Look at that notation I just wrote. I'm going to let k start at 1, and I'm going to just change this k, and I'm going to stop at n. So what does this look like? A r sub 1 plus a r sub 2, the area of rectangle 3, the area of rectangle 4, 5, 6, all the way till I get out to the area of rectangle n, which is just all of these guys over here, right? That's what that is. That's the sigma notation for this. Still there? But look, everyone, that's just equal to, and this is the part that is really, really awesome. That is just equal to sum k equals 1 to n of f of a plus, remember how I said in this formula right here, the only difference between these is that number in front right here. That's the only thing that changes. So what I can do is I could put here a k times b minus a over n times b minus a over n. Think about what would happen. If I start at k equals 1, this would be f of a plus one of these guys times the width. That's the first one, right? Then I let k be 2. That would be f of a plus 2 of those jumps times the width. That's the second one. And then 3 and 4 and 5. Do y'all get that?
Yeah, that makes sense.
You don't need, we don't need to get bogged down on the actual, like, okay, how the hell would you compute this? Okay, I don't want you to think about that. I want you to think about the notation. Just, do you understand the notation? Yeah. So this would give you the approximate area with n rectangles, right? With n of them. But how many rectangles do we need to get a very precise answer?
Infinity.
More, right? Infinity, right? Infinity. We need an infinite number of them. So why don't we take this formula and let's create a new formula. A new formula. This is our new formula. I would like to know what the limit as n goes to infinity of the sum k equals 1 to n of f of a plus k times b minus a over n times b minus a over n is. Because whatever this limit is, it's like I'm trying to find the sum of an infinite number of rectangles. Make sense? What the hell is that? Well, it's something, right? It should give me a numerical answer. It's a limit that I'd have to calculate, and these limits are very hard to do by hand, okay? It's okay, though. That's what I'm interested in, right? I just really want to make sure you understand that this right here represents the idea of taking an arbitrary function, right? Take an arbitrary function and started at A, ended at B, cut it up into n rectangles, and then let the number of those rectangles go to infinity. And that should give us the true area if we can calculate that limit, right? If we can calculate the limit. So we should come up with some notation for this, right? This is a lot to write, right? This is a whole lot to write. So maybe there's a more condensed way I can write this that would make it so that you know what I mean, but I don't know. So how about this? Instead of me writing all of this crap, you all agree that that's just the height of the function? Each one of those is just the height of the function. So it's just the value of the function at some point. Why don't we just kind of abbreviate it with f of x? Okay, we'll just, yeah, that's the height of the function. And then this right here, this is the width of each of the rectangles, right? It's the width of each one. It's how much the x changes each time, right? It's like a change in x. But I'm going to have an infinite number of them, and they're going to get really, really small. So I'm going to call it, I don't know, let's call it dx. And then this right here, all this crap out front isn't really a true sum. It's not just sigma, it's the limit of a sigma. And so we can't call it sigma, we can't just call it a limit. I don't know, let's give it some special symbol. How about this symbol, which is a sum, the S letter stretched out. It's now that stretched, what S means like a limit of a sum. And then I need one more thing. I accidentally didn't give myself enough room here. Okay. This was that, this was that. I need one more thing. I need somehow to let you know that this function starts and stops at some point A and B. So what I'm going to do is add one more thing. I'm just going to put an A here and a B here. That way you know I mean to only look between A and B. Now you know where the integral sign comes from. The integral sign comes from the idea of a Riemann sum, which is really the idea that you're going to take the sum and you're going to let the number of rectangles go to infinity.
But Professor, isn't
yes,
there like other types of ways you can find out other things? Like, why does this take overhead of all the other ones? Does that make sense?
Wait, what?
So isn't there other ways you can find like the area underneath the surface, or like the area of something? Why does this take leeway over all those other forms?
Well, I'm not sure what all other ones you're referring to. This covers any curve, like covers curves, right? Of course, if these are straight lines, we have formulas. I don't know if that's what you're referring to. You're saying other ways of finding areas. I'm not sure what you're referring to.
So for example, like spheres, like well, I don't again, I don't know, but like, yeah. I thought series was another way for you to find area underneath curves. Like I thought there's like several other ways. Why does this one take leeway to like the old?
Because it covers any function. Like a sphere is a specific, very, very well-behaved shape, right? A sphere, a circle, they all have like the same, what we would call curvature. Okay, but an arbitrary function can do all sorts of things, and this formula will cover it. This covers it. And so it's very powerful because it's very general. Again, without knowing exactly what you're comparing, if you're comparing it to like formulas we already know, then yeah, this is way more powerful because it covers everything. So now I have not, look, all I have done here, okay, this first 40 minutes of class, all I have done is established for you where the notation of the integral sign of the integral comes from. Okay, that the integral from now on, when we look at this sigma, this integral sign means we're adding up a bunch of stuff, right? We're adding up an infinite number of things. What are they? Well, it's the height of the function times this width of some arbitrary rectangle. Height times width gives us that area. Understand? Later on in this class, we're going to be rotating functions around axes and doing cross sections and doing things. And you're going to need to understand that it's all about setting up a formula that gets that volume or whatever it is you're looking for. It creates that for you. And so you need to understand how the integral works with that. So you will get to it. We'll get to it. I don't want to get ahead of ourselves. But right now, we just have a symbolic meaning of this now, right? We just know that this has symbolic meaning. How do you actually calculate it? Like, how do you do it? How do you get the freaking answer? Because nobody wants to do this calculation. It's so hard to do. It's so hard. It's very tedious. And then you have to do a limit. It's really, we could spend weeks on this. We don't need to. What?
Isn't b minus a already a derivative, like the change in? Isn't that a delta already?
B minus a over n is a,
Isn't that a delta already? Like a
it's the change in x. It's this right here is our change in x, right? The reason we write dx is because of the limit. When we let n go to infinity, that delta x goes to 0. The width of the rectangle approaches 0. It becomes infinitesimally small, right? Think about it. You have more and more rectangles, you get something that gets infinitesimally small. And so we don't call it, once we pass it through the limit, we call it dx now. We don't call it delta x anymore.
Sir, I have a question.
Yes.
I've heard before that it's impossible to find the area underneath a curved line. Is this just a really good estimation, or is this the exact area?
It's the exact area.
Okay.
Because it's a limit, and we know that that limit will approach a certain number. And it approaches one unique number. It doesn't approach anything else. And so if you were to do the calculation by hand, you would never actually truly get there, because you would have to stop at some point, right? Like, you could not let n be infinity. You would spend the rest of your life and die and never get it. But the limit allows us to see what it's headed towards, and there's only one number it can head towards. And that goes into something called the completeness axiom that has to do with our number system, that if you have a convergent sequence of numbers that's headed somewhere, it can only go to one place.
I got
And that's beyond the scope of this class, but we have to have the completeness axiom to be able to say that, which we do. The real numbers are complete. So, okay, now we have no idea how to do this, right? We have no idea how to actually use this. We just know what the notation means. But then comes a very important theorem, okay? So important, in fact, it's called the fundamental theorem of calculus. The fundamental theorem of calculus. You may not know this, but there was actually a fundamental theorem of algebra. When you were taking algebra, there is actually a fundamental theorem of algebra. It has to do with, if you are given a polynomial function of degree n, that you are guaranteed that there are n roots, as long as you're allowed to look in the complex number system. But we don't deal with complex numbers. So that's why we don't talk about it too much, college algebra, because it requires that you accept imaginary numbers and delve into them pretty deeply. But there is a fundamental theorem of algebra, and then there's a fundamental theorem of calculus. And then even within calculus, there's more theorems that are fundamental. But this is the big one. So here it is, right? You ready for it? This is the big theorem. It is going to allow us to do the calculation like this, okay? Like this. So here's the way the fundamental theorem of calculus works. I'm going to put fundamental theorem of calculus, FTC, okay? I don't want to write it out. Do I have to? Fundamental theorem of calculus? No. Here's what it says. The area under some function f of x on the interval AB is, well, first of all, let's write the notation. It's this. This is the way we write it. Again, that's just reminding us that it's this limit of this summation, right? But the fundamental theorem of calculus says that what this is simply, and I'm going to leave a blank space in between for a reason you'll see in a minute. All it is this: capital F of B minus capital F of A. We need to understand here where F, capital F prime equals little f. In other words, if you want to know the area under some function, little f of x, between a and b, if you want to know that area, all you have to be able to do is find capital F, which is the antiderivative of it. If you can find the antiderivative of this, then all you have to do is plug the right endpoint into the antiderivative and subtract from it the left endpoint plugged into the antiderivative and just give me the numerical answer. And whatever that
Why?
answer is the area.
Why? Because the limit is already applied inside of the antiderivative, or?
I proved the fundamental theorem of calculus as a third-year math major. The proof of this is beyond the scope of this class. You just have to accept the theorem. It's not an easy theorem to prove, okay? The book does have a proof, but it's, yeah.
Not a fun one to go over.
Well, I think
Mickey Mouse.
a true rigorous proof in math requires what we call delta epsilon proofs. And unless you know how to do delta epsilon proofs, it's really, you know, it's, let me see here. You're just going to have to accept this, all right? It's a beautiful theorem. It's fundamental theorem of calculus, okay? Let me see here. Fundamental theorem, calculus, delta, or delta epsilon proof. Okay, oh, here we go. God, I wish I had this when I was in school. Let me see. No, that's, no. Let's see what this looks like. I don't know about this. No. That's just the limit. That's not the delta epsilon proof. Okay, yeah, I don't want to take up time. It's ugly. I'll try. I'll go look. I have it in my notes. I kept all my notes, of course. So I'll look it up and maybe I'll just push it out to you and you can see it. All right. We're just going to take it on faith. All right. So in order to do this, in other words, if we want to find the area under some function, we have to be able to calculate the antiderivative, right? First. And then we're just going to plug in the two endpoints, which is why we spent so much time learning how to calculate antiderivatives or do antiderivatives, because we need it for the fundamental theorem of calculus. So I left a blank in between here. And the reason I left it blank is because the common notation for this is that to first, remember, you have to find the antiderivative. So what we do here is we put capital F of X, which just tells you, hey, go find the antiderivative. And then we put what's called the evaluation bar here. We put an A and a B here. And that just reminds you, okay, you're going to have to plug B into this and then subtract what you get when you plug in A. Let me show you an example right underneath this. As an example, let's say I wanted to do this. Go from 0 to 3 of x dx. This means if we were to look at this function, f of x equals x, between 0 and 3, I want to know the area. So the very first thing I'm going to do is find the antiderivative, right? This is the black bar. So what's the antiderivative of x?
1/2 x squared.
Yeah, let's not crumble now, everyone. Right, 1/2 x squared, just a simple antiderivative, right? So that space right there just gives you an opportunity to write the antiderivative down. Okay, so there it's written. Now I still need to now plug 3 into it and then plug 0 in. So my next line, or my next part of this is going to be, okay, I'm going to take 3 and plug it in first. So 1/2 times 3, sorry, I already squared it, times 3 squared. And then that's me plugging in the B into the capital F. And then I do 1/2 times, now I plug in the 0 to the capital F. And this gives me 9, and then half of 9, 9/4. I'm going to put 9 over 4. I'm sorry, 9 halves. Sorry, 9 over 2. And then minus nothing. So my answer is 9 halves. That's the area. the exact area. Now, if you don't believe this, that this actually worked, we can verify it geometrically, because this function is very simple. It's the identity function, isn't it? The perfect diagonal line, that's x. That's f of x equals x. And we were looking between 0 and 3. So we were looking for this area in here, right? And this is a triangle. So I know that the area is 1/2 base times height. Well, the base is 3 and the height, well, we plugged in 3 and it spit out 3, right? That's how tall that point is right here. So that's 3. So the area of that is 1/2 times 3 times 3, which is 9/2, which checks out, right? It checks out.
I would say this is one of those ones that for the sake of my brain wrapping around it, I convert it into a decimal in it. You know, because
Yeah,
when
I
I see,
mean,
oh, nine halves square units
Yeah, most of the time we'll do
versus
it.
4.5, which is like, oh yeah, it's 4.5.
In the real world, you're most likely doing decimals, but okay, so here's what I want you to do. I want to see, go back to the very first problem that I presented to you, where I was showing you this animation right here, where we were cutting this up. Remember, we said that the answer here was 41/3, or sorry, 41 1/3. This was the function x squared between 1 and 5. So come on, get back here. Between 1 and 5, I want you to find the area underneath x squared. And in case you need it, I'll grab this and put it here. This should not take you more than 2 minutes. Give me a yes on the vote. Give me a yes on the vote whenever you're done. Okay, I think most of you are done. That's good. It shouldn't take that long. Did y'all get 41 1/3?
Yep.
Or would it be 120?
124 over 3.
124 over 3? Yeah.
Yeah,
Right.
some gross number.
Yeah. Exact area. Okay. If that doesn't blow you away, I mean, it's crazy, right? That all it requires is the antiderivative and you can find the area of underneath any curve.
This one is like when I was going through calculus the first time, and it just made me pissed about how hard it was to find everything in geometry.
Yeah.
It's like, that's so easy.
Yeah, exactly. It makes things, it's weird. Here's I don't want to bog ourselves down on this, but I just want you to really truly understand what the fundamental theorem of calculus is telling us. It's saying, and this is just amazing, okay? It's saying that if you look at the function like f of x equals 2x, and you look between 2 and 6, and you want to know this gray area, right? You want to know what that gray area is. What you actually do is you look at the antiderivative, which is just x squared, and you look at the difference of the y coordinates. It's this y coordinate minus this y coordinate, that distance right there, up and down. That up and down difference on the antiderivative is what the area here is. It's pretty crazy. Look at this one, saying there's a different example. If I want to know the area underneath 3x squared between 2 and 4, then what I do is I look at the graph of x cubed, and I take the difference between the y coordinate, the two y coordinates here, and that will correspond to that area. Pretty awesome. Again, we're not proving it, okay? We're just going to take it on faith. All right, we need to get some language in order here. Oh, where did that go? Okay, so in our notes, I do provide all this to you. So if you wanted to go back and look at it, here's that formula. Okay, this right here, it's there. Now, this is called the definite integral of f from a to b. Everything we've been doing before, we didn't have the numbers on the top and bottom of the integral sign. Those were called indefinite integrals. And when you do an indefinite integral, you're always going to get the antiderivative plus a constant. And it gave us a family of functions. The definite integral returns to you a numerical value. And it represents the area under the curve. All right. So it's kind of like apples and oranges. Indefinite returns function plus constant. Definite returns number.
This is one of the questions that I had earlier in my last calculus class, is that plus c really doesn't like matter when you take the integral. For example, like plus c will change the y-intercept, which is like where.
Okay, yeah, let's go back to this one. Okay, remember when I did this and we said let's find an antiderivative here? We could have said plus 4. That still would have been an antiderivative, right? But then when you come over here, it would do a plus 4 here and a plus 4 here. And then when you subtract, this 4 and that 4 will cancel every time. If you would have done plus 10, it would have been plus 10, and that minus would have canceled.
Oh, snap. That makes
See
sense.
what I'm saying?
Oh.
And if you want to generalize it, if you would have said plus C, and then plus C, then you would go plus C minus C, and they're gone. So it will have no impact on the numerical answer. Good question.
That's pretty cool.
Yeah. Yeah, this
that
antiderivative can be any antiderivative you want. So we usually pick the one that has plus 0 because it just keeps things simple.
But that doesn't make sense. Wouldn't the area be completely different if it was 5 feet up as opposed to not 5 feet up?
No, because look at this picture I showed you right here. I said that this area is just the difference of these y coordinates, right? So if I shift this graph up, right? If I take this plus C, if I move the graph up, the difference of the y coordinates is still the same, right? This number is still the same as this number.
No, but you still got that whole bottom. You still got to go all the way down.
No, it's the difference of the y coordinates. It's okay, look at it this way. It's this height all the way to the x-axis minus this height from here to here, which gives you this height from there to there. If I do it on this one, it's here to here minus, here to here, right? This is capital F of B, this is capital F of A, and their difference is still this, right? You still have the same difference because all you've done is moved it up or down.
The C gets subtracted out and cancels.
That's right. The C is insignificant.
Oh,
Lewis, does that make sense?
No, there's a piece. Okay, so you still have that height difference. So like so what happens to that bottom like area that you've taken out?
No,
Does that make sense?
see, here's the thing. You're thinking about areas over here. We're not thinking the area of this. The area of this is equal to the difference of the y coordinates on the antiderivative. Don't think about areas over here. We're not talking about areas. We're talking about difference of heights of points, not areas all the way down to the x-axis.
That's so confusing because we literally just went over the principle of just taking areas to an infinite amount, and now you're saying like, oh, we're not worried about that anymore. We're worried about.
No, I'm not saying that. I'm saying that to find the area under some curve, look, this curve over here is 3x squared, right? To find its area, all we have to do is go look at its antiderivative, and then look at the difference of the y coordinates. So I'm not looking at the
Okay.
same function, right? One of them is f, the other one is capital F, it's antiderivative.
So it's like the difference between velocity and position time. Okay, that makes sense.
Yeah, you could say it this way. I mean, that's exactly, I'll reframe it that way. Look, let's say that we have, what if I tell you that this is time and this is velocity? Okay, and I give you some curve like this, and let's say we start here at A and we end here at B. Okay, then the area underneath this, to find it, we would need to take the antiderivative of velocity. What's the antiderivative of velocity?
Position time.
Position, right? Position. So this is position and this is time. And so whatever the antiderivative is, you look at the y coordinate there, the y coordinate there, whatever that distance is, that's capital F of A. This right here is capital F of B. And so the difference of those two is this. This right here is equal to that area. And what is the unit? What would the unit be here? Well, we would need to know if position we can measure maybe in like miles. So this right here, our numerical answer would be miles, which means that this area would correspond to how far you went. So like if you know your velocity at every point in time, then the area underneath the velocity curve will give you the total distance you traveled.
That makes sense.
Yeah. Okay, let's go back to these notes here. All right, so here's the fundamental theorem of calculus, right? There's actually two versions of the fundamental theorem of calculus. I am presenting you with what's called the evaluation theorem, which is one of the two. This is the one that we use. So it basically says, again, if you have a continuous function on a closed interval, then this is equal to the antiderivative with that little evaluation bar, which is just f of b minus f of a, where capital F is any antiderivative of little f. All right, I want to do another example. I want to know this. Tell me when you're done. After you do it and get an answer, I want you to draw a picture of the area that you just found. And then see if your answer makes sense. Still giving a few people a little time to kind of follow through that. All right. So did anyone have trouble getting 0? Everyone got that?
I was getting obscenely small decimals, but pretty much 0.
Were you using your calculator for something?
Yeah, I realize I should have been able to just realize 2 pi is 1.
Yeah. Okay. So
But
you were probably in
Calculator puts out 0.99.
I bet you're in degree mode, and that's why. Because
Hey,
you need to be in radian mode. Then it would have gotten you 0. So here, check out what's happening here. We are taking the sine function. Now we all should know that the sine function is periodic and it goes through one period between 0 and pi. And we were trying to find the area underneath, and it gave us 0, which means, Lewis just mentioned this in the chat, that this means that it's counting that the area below the x-axis is counting it as negative. Which is weird because we usually have never had like negative area, right? Area is always positive. But you can convince yourself it's true if you think about this. When you're over here drawing those rectangles, right? Of course, the width is a positive number, but what about the height? Here, the height is a positive number. So you get a little width times a positive height and you get a positive number. But over here, when we're drawing the rectangles, now your rectangles go down. And when you plug some value into the function, it's spitting out a negative number here. And then you multiply that times the width, which is positive, and so it calculates it as a negative. Remember, the height is the height of the function above or below the x-axis. So if it's above, it's positive. If it's below, it's negative. The sum, the integral doesn't know that. It doesn't know how to distinguish where you're above or below. So this can be problematic. Do you all agree? Like if we really wanted the true like positive area of everything here, the way we would have to do it is we'd have to recognize from the graph that we have x-intercepts. And then what we would do is this. We would do, there's a couple ways to do it, but here's one way we could do it. We could say, let's do the area from 0 to pi first of sine x, right? dx. And then what we're going to do is we're going to realize that if we go from pi to 2 pi of sine x dx, we're going to realize that this is going to be negative, right? And we don't want to count this as negative. So what we do is instead of adding this area, we will subtract that area. So it's like we know this is going to spit out a positive number. We know that that's going to spit out a negative number. But by subtracting the negative, it's going to wind up adding it. Make sense or no?
So we should just see it.
Pardon?
So we should just naturally see it. Sorry about that.
Well, yeah, we will have to factor in that sometimes you have x-intercepts. So you do have to worry about, if you're asking, look at the answer to this question is 0. That is the answer to the question. But if somebody asks you, hey, but give me the area of these two, if we're counting everything as positive, then you'd have to break it up. Another way you could do it, is use the symmetry and just do this. Go from 0 to pi and double it. Double that answer because you have symmetry. You know that the top arc of that sine function, that area is equivalent to the bottom arc of the sine function. So you can just double the top arc and you get the same answer.
So 0 is just the correct answer though?
0 is the correct answer. If this problem is posed to you like this, the answer is 0.
Okay. That's weird.
It gives you the net area.
Okay, so the fact that it's negative area is capable of occurring, I guess, in mathematics.
That's right. It's like you're tallying up a check, like a
Yeah.
bank account, and you got some deposits and some withdrawals, and then at the end, if you get 0, then yeah, then broke even, right? Okay, let's look at another one. How are we doing on time? We got time? All right. So I want to do another one. Okay, how about this one? The integral from 0 to 2 pi of x cosine x. And just to show you what we're doing here, this is the actual graph of x cosine x. This is the graph. And I'm not asking you for all these areas considered to be positive. Okay, I'm just asking you for the integral, the definite integral from 0 to 2 pi. So give me the net area. Count the positive as positive and the negative as negative. Okay, we're going to try and find out the net area of this thing from 0 to 2 pi. Well, the first thing we need is the antiderivative, right? Unfortunately for us, this antiderivative is not simple. So I'm going to come over here and I'm going to do this as an indefinite integral first. That way I can do any work I need to do. And then once I get this answer, then I'll come back to this. And this here is integration by parts. I'm going to let u be x. I'm going to let dv be cosine x dx. Du is dx. And v is sine x. And so this turns into ultraviolet minus the integral of voodoo. So this becomes x sine x minus the integral of sine x dx. And the antiderivative of sine x is negative cosine x. Be careful there. And then that becomes x sine x plus cosine x plus c. Okay, so we had to do some integration by parts first. And that's an integral that we did weeks ago. So that you may not have recognized it right away, but I expect that, yeah, now that you see, yeah, you're good with that. So then I come back over here and I say, okay, so what I need to do is I need to take x sine x plus cosine x, and I need to evaluate it at 2 pi and at 0 and subtract. As long as I've been doing this, I've always liked to do 2 big sets of parentheses where I first plug in the 2 pi and then plug in the 0 and just kind of keep them separated. So this is 2 pi sine 2 pi plus cosine 2 pi, and then minus 0 sine 0 plus cosine 0. And yeah, you need to know what, sine of 2 pi and cosine of 2 pi are. So this will be 0, sine of 2 pi is 0, plus cosine of 2 pi is 1. And then minus, let's see, this is 0, and then cosine of 0 is 1. And so at the end of the day, you just get 1 minus 1, you get 0 again. It just happens to be 0 here. It's not always going to come out to be 0. All right.
Every area under the curve is 0. That's what I'm seeing here.
Yeah. What we're saying is that whatever this positive number is and this positive number, this is a negative number. These 2 areas together are equivalent to that area here because they cancel each other out completely.
So with like sines and cosines, is that just kind of a thing that happens with them a lot? Or is that just these are weirdo cases?
It's just this is the example I gave. If I would have gone from 0 to pi, right? If I would have gone from 0 to pi, we get a different answer.
Okay, but it's a possibility when you're dealing with some of these.
Yeah, it's possible with sines and cosines to get 0. Okay, y'all got the general idea? What's that?
Is it possible with other formulas
to get 0?
Yeah.
Oh yeah, absolutely.
Okay.
Yep. Yeah, you could have it with a parabola. If you have a parabola drawn just right, the top area could cancel out the bottom, and
basically as long as it goes under the x-axis, then there's a possibility.
If you got some positive, so some graph above the x-axis, some below, then it's possible to get no area, no net area. Okay, we need to talk about some properties of this definite integral. There are some very important properties that we need to understand. The first property says that if you do an integral and you go from a to a of any function, the answer is 0. Does that make sense? I mean, you've got a function and you're starting at a and ending at a, right? So you got some function here and you're only looking at the area right there below a. And that should have 0 area because it's just like a single line and lines don't have areas. So you notice we don't have an interval. It's a to a. That seemed to make sense, reasonably speaking, yes? The second property says if you go from A to B, okay, so this property is saying if you go from A to B and you want to find the area underneath the curve, that what you can do instead is go from B to A, switch the order, but then you have to switch the sign out front. So reversing we call these limits of integration. Reversing the limits of integration changes the sign of the integral. The next property says that if you're doing the integral of a constant, then all you have to do is take the constant and multiply by b minus a. And that's just because if you think about it graphically, if this is a constant function, then the height of it is k. All you have to do is figure out what b is and what a is, take the difference of b and a, and that'll be your width times the height, and that's your area. Now for us, we really won't do this. Let me show you an example. If I want to do the integral from 1 to 5 of, let's say, 4 dx. Okay, if I'm going to do this problem, here's how I'm going to do it. I'm going to take the antiderivative of 4 and put 4x. Then I'm going to put 5 here and 1 here. And then I'm going to plug in and get a numerical result. So when I plug in 5 into there, 4 times 5, I'm going to get 20. When I plug 1 in there, 4 times 1, I'm going to get 4. This will be 20 minus 4, which is 16. The area is 16. This formula says instead of doing that, you could have just done 4 times 5 minus 1 is 4, so 4 times 4 is 16. I mean, just do this. This isn't that bad to do that. So, but it's a property, so I'm putting it here. Questions? May I proceed? All right, the next one is something we should recognize, that if you have a constant in the integral, the constant can come out. Right? I mean, we've seen that before. For definite integrals, same thing applies. We have a number inside, we can pull it out. So that should be nothing new. The fifth property is actually pretty, I think it's pretty easy to understand. If your function is above or equal to the x-axis, right? If your function is a positive function above or equal to the x-axis, then you should expect that the area is a positive number or 0. As long as the graph is above the x-axis, then you should get positive area. On the other hand, if the graph is below the x-axis, then you should expect your area to be negative. That seem reasonable? This next one I've kind of already used, but this is the formal rule for it. This property says if we start at A and we want to do the integral that goes from A to B, right? If we want to do this integral, it is completely up to us. We can, if we want, if we choose to, we can pick any value between A and B, C. We can pick any C between the A and B. And instead of going from A to B, we can go from A to C, do that area, then add to that the area from C to B. So instead of finding the area of the whole thing, we can break it up into 2 pieces and do 2 individual areas. It may seem like, well, why would you want to do that? Just, you'll see. There's going to be a reason for that later. But does it make sense to you? Like this is that, and this is that. And so you're just adding those 2 areas together.
Is that how we
Question.
can also subtract from certain intervals?
Say again?
Is that how we could also subtract from certain intervals? Like
Subtract.
for example, that cosine, we know that from, let's say the integral of, let's say from pi to 2 pi, sine is going to be negative. So we can just take that piece out. Does that make sense?
In relation to property 7?
Yeah, so we can, instead of just adding that, we can subtract. So we can go from C to A and then subtract from B to C.
Well,
Does
that's,
that make sense? I don't know.
well, what we could do is, this was the one we had, was integral 0 to 2 pi of sine x dx, right? And the answer we got was 0. This property says we could have gone from 0 to pi first, right? And then we could have gone from pi to 2 pi. And if I do that, I'm still going to get 0. That's what this property is saying. What you're referring to is, I said, if we're trying to find like the total area, not the net area, then what we have to do is realize that this is a negative. From pi to 2 pi is negative. So what I said is, instead we would subtract that, right? We'd subtract this in order to get it to spit out a positive number, not cancel out. So it's not really property 7 that I mean, in some way it is, because we split it into 2, but it's not, the negative there is not in this property. Okay, time, we're good. Okay, next one. Remember what it means for a function to be even. Even means it is a reflection of itself over the y-axis. So all even functions look like reflections over the y-axis. So if I take that, I reflect it over the y, it lands on top of it, right? Like that. That's an even function. This property says, and be careful here, if you go from negative a to positive a, this is not a to b, this is negative a to positive a. So if I go from some negative a to some positive a, and I want to know the area, because it's an even function, I can just look between 0 and a, right? 0 and a, find that area and double it. Right? If I'm going from negative a to a on an even function, just go from 0 to a and double that answer. This would work for cosine as an even function. Right? If you go back to pre-cal, cosine looks like this. That's cosine x. And that's an even function because when you draw it the other way, it looks like this. And it's a mirror image of itself over the y-axis. So if I wanted to go from like negative 3 pi to, let's say, like 3 pi, instead what I could do is go from 0 to 3 pi of cosine x and then double it. That would be the same as going from negative 3 pi to 3 pi of the function. This is not a very, it doesn't come in very often, but there are some homework problems where this comes up, all right? Now, what about an odd function? Do you remember what an odd function looks like? Odd functions are reflections over the origin, which means it's a double reflection. All odd functions are reflected over y and then x. So this is an example of an odd function. And is it obvious to you that if I go from negative a to a, that no matter what, it's going to cancel itself out? Even if I went here, even if I went negative a here to positive, no, that's not a very good color. Even if I went negative a here to positive a here, and I wanted to know this area here along with this area here, that would still be 0 because they just wipe each other out. But it has to be an odd function for this to happen.
Sine's odd, right?
Sine is odd. So on your homework, if you see a problem that is causing you an issue where you can't find the antiderivative because it's too hard, like oh my God, I've never seen that before. That's crazy. The thing that'll tip you off is if these numbers here are the same numbers, except this one's negative and this one's positive. If it's that, then most likely this in here is an odd function. If it's odd, then you can just tell me the answer is 0. You don't have to do any work. How do you show a function is odd? Does anyone remember how to show a function is odd?
You set the negative inside.
That's right.
The x.
Odd means this. Odd means when you plug negative x into the function, you get exactly the same thing as the function, but putting a negative in front of it. That's how you check to see if something's odd. I should show you an example. Let me show you that this function is odd. Let me show you that this is odd. So to do it, here's what I do. First, I plug in negative x. When I plug in negative x, I'm going to get negative x cubed plus negative x. When I cube a negative, I'm staying negative. And when I add a negative, I'm going to be subtracting. So I look at this. This is f of negative x. And I notice that this is almost f of x, isn't it? It's actually this with a negative multiplied through. So it's the original function, but with the negative applied to it. So that would make that negative and that negative. Then they match up. And since this equals this, it's odd. You might have to review that.
Most definitely.
Okay, so here are the homework problems. Now, let me kind of look through this real quick. 289. 289. 307. So I have good news and bad news here. What I'm asking you to do here is kind of go back to the, well, with the exception of the first two, I think these two are new. But these problems right there are problems that are in sections from chapter 6, where I told you to do them and I said, ignore the numbers. Remember that? I said, ignore the numbers. I'm basically asking you to go back now, and now that you know what to do, you've already done the antiderivative. So all you have to do now is do the fundamental theorem of calculus and just plug the two endpoint numbers into the antiderivative and subtract and get a numerical answer. So there's really not, I mean, since you're all really good at antiderivatives now, right? There's not a whole lot that we've added to this. We've only added just plugging a number into it, right? Two numbers and subtracting. Okay, any questions?
So these are just previous homeworks?
Yeah, I recommend that you go back and just kind of, I would try and do these. This is not the, I'm not giving you the entire homework set from before. I'm just asking you to go take a look at some of the older problems you did and kind of complete them now that you have the numbers to plug in.
All right.
Okay. Okay, I have 10 minutes, so I want to talk about something to lead us into somewhere where we're going with this. It's on topic enough, I guess.
Could I look at that homework for just a second more?
Yes.
I want to write all that down.
Yep.
Okay.
Everybody, I hit 12 pounds today.
Like
So,
burned?
I'm 12 pounds lighter than I was 3 weeks ago.
Hell yeah, man.
The first 4 are easy. The other 8 were hard, but
Nice.
so I reached my goal already, but I mean, my ultimate goal is takes me into like May. So, but I reached the goal that I told you for your 5 points. So that's good. I need to set a new goal now.
What is your ultimate goal? You have one?
175.
Nice.
That's my goal. That's the weight. I'm 6'1". My wife doesn't like that weight. She likes me at like 185, but I feel better at 175.
Hey, that's what's important, man.
So we'll see. When I was doing triathlons, I was 158. I was like it was kind of gross,
Oh.
actually.
Yeah,
Kinda gross.
Joaquin
But
Phoenix, man.
it's all about power to weight ratio. It's all about how much power you can generate and how much weight you have to carry around with you. So, all right, here we go. You all ready? I'm going to just talk for a few minutes about something. This has to do with statistics, which is tied into the definite integral, right? So in statistics, we have something called discrete versus random in terms of variables. Okay, so when we're talking about statistics, we have basically discrete random variables, and I mean, sorry, that's not random, sorry. This is supposed to be continuous. We have what are called discrete random variables, and then we have continuous random variables. And so there's a huge difference between the two, and I want to explain what they are. So let me give you an example of a discrete random variable. Let's say that I take a 6-sided die. Okay, whatever. I don't know how a die looks, but I'm just going to make it. There's a 6-sided die, right? And I'm going to create what's called the probability density function. Let me just do it first, and then you'll understand what it is. Right here, this is going to be where I list what outcomes are possible. And then here is going to be the probability. All right, so when I roll a die, I could roll a 1, right? I could roll a 2, I could roll a 3, I could roll a 4, I could roll a 5, or I could roll a 6. Right, on a 6-sided die. And so the probability of each of these is, let's see, the probability should be 1/6, right? If it's a fair balanced die, the probability should be 1/6. So if this is 1, 1/6 would be down here somewhere. So if I plot this at 1, I'd be at 1/6, at 2, I'd be at 1/6, at 3, I'd be at 1/6, at 4, I'd be at 1/6, at 5, I'd be at 1/6, and at 6, I'd be at 1/6. Make sense? What I'm going to do next is kind of strange, but just follow through with us. I'm going to create a rectangle out of this first dot. I'm going to go to the right halfway and down, and to left halfway and down. Halfway to the right, halfway to the left. By doing that, how wide is that rectangle?
1.
1. And how tall is it?
1/6.
1/6, right? And we got that? So what's the area of that rectangle? 1/6.
Just 1/6, right?
1 times 1/6. Now I could do that for each one of these. Halfway to the left, halfway to the right, down, that would have an area of 1/6. Halfway to the left, halfway to the right, down, that would have an area of 1/6. And I keep doing this for each one, right? And each of these would have a 1/6, right, probability. Here's the thing about statistics. The sum of all probabilities for some event has to be equal to 1. So there are 6 possible outcomes here, right? There's 6 outcomes, and each of them have an equal probability of 1/6. So if I take all of the probabilities and add them up, the fundamental rule of this, sorry, I don't want to say fundamental rule because it's not a theorem. I'm just saying the basic principle in statistics and probability is that the sum of all the probabilities must be 1. It has to be, okay? I'll give you another example of discrete random variable. Let's say that I have a box, and inside of it, I have 7 red balls, and let's say I have in here 3 green ones. Okay. So I'm going to pick one out, okay? I'm gonna pick one out. So let's look at the outcomes. What are the possibilities I can have here? What's the outcome and what's the probability of it? So when I pick a ball, I can either have what? Red come out. I can either have a red in my hand or I can have a green in my hand, right? That's it. Those are the only two outcomes possible. Now the probability I'm going to get a red, well, there's 7 of them in there, right? Out of 10, 7 out of 10. So I would write that as, you could write as 0.7 or you could write 7/10, however you want to write. I'm going to write 7/10. Here's 1. That's the probability of getting a red. The probability of getting a green is 3 out of 10, right? So that would be 3/10. And if I do that same thing where I go over, down, over, down, over, down, over, down, this would be 7/10, this would be 3/10. And of course, if we add those two together, you get 10/10, which is 1, right? Discrete random variables can only have a fixed number of outcomes. You roll a die, 2 outcomes. I mean, sorry, 6 outcomes, right? You pick a ball out of a box with 2 colors in it, you got red or green. If I ask you how many siblings you have, you're going to give me 0, 1, 2, 3, 4, 5, right? You're going to give me a discrete number. You're not going to give me half. You're not going to give me 0.7, although some of your siblings might not completely seem like full human beings to you. I don't know. But those are discrete. If I ask you how many people go to a Spurs game, right? That's a discrete random variable. It's a nice number. There's no fractions or decimals. So to find probabilities, right, or to draw these probability density functions, we have this idea here, right? You with me? 1 minute. Continuous random variable would be something like, how much do you weigh? Right? That's different because now look at the outcomes. Now I could ask you, how much do you weigh? Probability here. I could say, how much do you weigh rounded to the nearest pound? That would be discrete because you're either going to be like, 1, 2, 3, 4, 5, right? You're going to give me some nice number. But if we don't make it where you're rounding, then everyone can take on all these different weight values, right? Like you could weigh, I don't know, 184.2. And if you have a more precise instrument, maybe it's 2.5. And if it's more precise, maybe it's 2.53. And if it's more precise, 2.531, right? It really can, your weight is something that is, it's not as discrete as the dice outcome. Do y'all see what I'm saying? Not like 1 or 2 or 3 or 4. It's all these decimal values. So what is the probability that you weigh exactly some number? What's the probability that you weigh exactly some number? 0. This is a weird idea. The probability that you weigh exactly one number is impossible. What you have to do is think about it as a very, very thin, infinitesimally small rectangle. And then you can talk about an area and a probability. And so instead of drawing these boxes like I did here, what we do is we have a curve up here. Okay, we have a curve. The probability that you weigh 0 is 0. So that we can say. But this way you can't really say. It just gets smaller, right? The probability you weigh 300 pounds, I mean, there is a probability. The probability you weigh 600 pounds, there is a probability, right? And so now what we're interested in is the area under this curve. But here's what I can tell you. That area must be what? 1.
Oh yeah, all equal to 1.
It has to be 1. All probability density functions for continuous random variables have to have an area of 1 because it's the sum of all the probabilities together.
This is like a whole like percentile and standard deviation and
Exactly,
all that
standard
stuff.
deviation, all that. Z-scores, if that, I'm sure that sounds familiar to you if you're saying that. Z-score is all about finding where here a certain area is below or above some number. So you're trying to figure out where you are on that. And so we use what's called the bell curve or the standard normal distribution. But anyway, my point is areas under curves are used in statistical analysis all the time. And so that means you need functions that behave certain ways and they all have to have an area under them of 1. So I'll give you a better example of this when we get into next class, because where we're headed next class, you don't have much time to digest all this. What we're going to do next is this. We're going to go from like 4 to infinity now. So instead of looking at the area on a closed curve, we're going to look at the area from a point forever. Or we might go from negative infinity to infinity. Or
It has
maybe
to
we're going to go
equal
from
1.
negative infinity to a number or something like that.
But
Those
then
are
it
called
has to-
improper integrals. What's that?
But then it has to equal 1 since we're going
For a
for
probability density function in statistics, it has to be 1. Generally, no. So when I was saying area is 1, I'm only talking about probability density functions in statistics.
I have a
Y'all are
quick,
free to go. I'll hang
I
out.
have a quick question about that. The probability of your weight being any single number. You said
Yeah.
that it was 0, correct?
Yes.
So
theoretically, yes.
is it 0 or is it 1 over infinity? Is it approaching 0 or is it a hard 0?
It's a hard 0 because your weight can only be measured to a certain precision, right?
Mhm.
And so we know that we have an infinite number of decimals to go out, right? So if you ever are measuring and you stop somewhere, there's nothing that you can do to guarantee me that the next decimal is not, or the next decimals are just zeros the rest of the way.
Yeah.
Next decimal could be a 1. So as soon as you stop and say, I weigh 183.45679, when you stop, then I would challenge you and say, well, wait a minute, hold on. What if you had a more precise instrument to measure? It could be that the next numbers aren't zeros.
Yes.
So what we do is instead of looking at the probability at a specific point, we look at the probability on an infinitesimally small window. So maybe you say this. You say, what's the probability that your weight is between 183.4751 and 183.4749. Okay, and then what happens is on the graph, you have those 2 points, right? These 2 points are there.
And you have
And
the
you've got some
infinite points
function out
between
here.
them.
And now you can find the area, and that area will represent that probability. And that's
Okay.
just the definite integral from those 2 numbers, which you should be able to do.
Yeah.
Now, it's going to be whatever it is. The more narrow that window is, the smaller the probability. But if you open that window up to like, if you open that window up to like 20 pounds to 300 pounds, you're going to have a huge probability because most people are going to land between 20 and 300 pounds. Now, there are over 300 and there are under 20 because they're babies and stuff,
Yeah.
right?
Babies throw off a lot of averages.
Yeah, so normally we would do something like, adult males or something like that, or adult females. But the important thing is that the variable is continuous, not discrete. And so if you ever have a continuous, you must be able to do areas under curves as opposed to discrete, where it's just draw these little rectangles and add them up. It's not, well, it still can be problematic, but it's not as.
It's not, hey, go do calculus 2 before you even think about it.
Yeah, and you don't really, well, there's statistics. You can take statistics courses where you don't need a lick of calculus. And what they do is they go to graphs. They already have the graphs. They already have tables that show them areas. So like, let me see. Let me see. I'm trying to think of bell curve. Let me just do bell curve z-score. Let me see. Yeah, so this is like your standard normal bell curve.
Okay.
And so what you have here is, this is very simplifying it a lot, but it basically says like, if if you have a standard normal bell curve, the area under this is 1, okay? But if you wanted to know like the probability that you would be past 3 standard deviations, it's this area forever the rest of the way. And that area is 0.001. That's the
Okay.
area between, that's the area from 3 to the right is very small. So you have a 0.1% chance of being over there. Whereas if you go
Yeah.
here, you know, you've got the area there would be 19 or 0.19 and 0.19, 0.191 and 0.191. So those two together, this area, does that make sense?
Yes. Okay. All right.
And
It's just-
most in the real world, most things have a standard normal distribution, which is this bell curve. Most things, right? You take
Yeah.
people's heights, you take their IQ, you take their almost everything is standard normal distribution. Not everything though, but a lot of things are.
Yeah.
If you look at the results for my students in grades on tests, historically it's been this curve upside down, which is basically, you know,
A lot of people get high, a lot of
credit,
people get
a lot of
low, and
marks.
then 80's a
It's
weird
like an
one.
inverted bell curve. So it's not a standard normal distribution.
Yeah. That's actually really interesting.
Yeah.
Okay.
Yeah.
Well-
So I meant to say there is a non-calculus based statistics and there is a calculus based one where you have to be able to do integration and things like that. And that's a much harder stats class.
Well, if I ever take one, it'll probably be that one, but I don't think I actually have to take one. So
Yeah, you probably don't.
statistics is
not.
one of those. It's like, if I don't have to do that, I'm not going to, because everything I know about statistics with my layman's knowledge is awful and I don't want to deal with it.
Yeah.
There's